Using the Bronsted-Lowry definition, we defined an acid as a proton donor, so here acetic acid donates a proton, and that yields hydronium. And here H2O is the base because it accepted the proton. And here you have the conjugate acid-base pairs, whereas the acid loses a proton in the forward reaction, and the base gains a proton in the backward reaction. And here is a similar example, where H2O acts as the acid, so effectively water is amphoteric. Now we can write acid-base reactions in a shorthand form. So here we have hydrochloric acid reacting with water, and here is a shorthand notation where we emit the water molecule. So the hydrogen ion and hydronium ion are often used interchangeably. And to measure the acidity of a solution, we take the pH, where P of a certain value generally means minus the log of that value. So pH means minus the log of the concentration of hydronium ions, and pOH means minus the log of the concentration of the hydroxide ions in the solution. Typically, the concentration of hydronium in an aqueous solution ranges from 1 molar to 10 to the negative 14 molar. So if you take the log of these values, you get the range of the pH being from 0 to 14. Now sulfuric acid is an example that falls out of this range, which is also known as battery acid, and vinegar has a pH of around 3. So the pH of acidic solutions is less than 7, and basic solutions have a pH greater than 7. So ammonia is a base which has a pH of around 12. So the pH scale is convenient because typically you get concentrations of hydronium being quite small. So for example, in water it's 10 to the minus 7 molar. So if you take the minus log of this, you'd get a pH of 7 for fresh water. And we'll also be using pOH, and pOH is a similar concept, which is basically the minus log of the concentration of hydroxide in a solution. Water is amphoteric, so it can act as an acid or a base, and it can therefore self-ionize or auto-ionize, where two water molecules react to yield hydronium and hydroxide ions. And the equilibrium constant for this reaction is 1 by 10 to the negative 14 at 25 degrees. So now we can write this equation using the concentrations of the hydronium ions and the hydroxide ions. And this is equal to 1 by 10 to the negative 14 at 25 degrees. And we can take the negative log of this entire equation. So this term becomes 14. And then using the rules for logarithms, we can break this log up as follows. And therefore we obtain the following expression. And that's applicable at 25 degrees. So in pure water, the concentration of hydronium and hydroxide ions is the same. So you'll have the following expression. And if you take the square root of both sides, which is a concentration of hydronium and hydroxide in the solution. So therefore, the pH is equal to pOH, which is equal to 7 in a neutral solution. As we've seen, the equilibrium constant is temperature dependent, and in the case of the auto-ionization of water, which is an endothermic reaction, so we add heat to the reactant side, and therefore an increase in temperature would cause a shift to the right by Le Chatelier's principle. And consequently you get more products being formed, and the equilibrium constant of water will increase with an increase in temperature. So we can see that when the temperature increases, the pH and pOH decreases because the concentration of hydronium will increase, and so will the concentration of hydroxide at the same time. So note that water remains neutral at different temperatures, and therefore the following relationship still holds, where the concentration of hydronium and hydroxide ions are equal, so therefore pH is still equal to pOH, except this term here will be different because the equilibrium constant is different under different temperatures. The pH of a solution of vinegar is 3 at 25 degrees Celsius. Calculate the concentration of hydroxide ions in the solution. Well, we can use the following relationship to find pOH at 25 degrees, and substituting for pH, we can obtain pOH. And that's equal to minus the log of the concentration of hydroxide ions in the solution. And solving this gives the following result. The molecules of a strong acid completely ionize in an aqueous solution to produce hydronium ions. And we can see this better using the shorthand notation. And here we have sulfuric acid dissociating into protons and sulfate anions. So therefore, for example, if we're given the pH, then we can use that to calculate the concentration of hydronium ions in the solution, and then using the mole ratios, we can easily calculate the molar concentration of sulfuric acid. And common strong acids to be familiar with are hydrochloric, hydrobromic, hydroiodic, and we have perchloric acid, nitric acid. So we call these monoprotic acids. And the other strong acid to be familiar with is sulfuric acid. So this here is polyprotic, and specifically this one's diprotic because there's two protons. Strong bases completely dissociate to produce hydroxide ions in an aqueous solution. And for example, if we're given the pH of the solution, then we can use the following relationship to find pOH, and then from that we can obtain the concentration of hydroxide ions in the solution, and then using the mole ratios we can obtain the concentration of sodium hydroxide. Or alternatively, you may be given a concentration of sodium hydroxide and you can find the pH of the solution. Now the common strong bases to be familiar with are the hydroxides from the alkali metals and the alkaline earth metals. So from group 1 we have lithium hydroxide, sodium hydroxide and potassium hydroxide, and the strong bases to be familiar with from group 2 are calcium hydroxide, strontium hydroxide and barium hydroxide. And you can use the group in the periodic table to determine the charges on the cations, where the hydroxide anion has a -1 charge. A 25 ml 0.05 molar aqueous solution of sulfuric acid is added to 100 ml of distilled water. What is the pH of the final solution? Well, being a strong acid, sulfuric acid will fully dissociate in an aqueous solution, and given these values, we can find the number of moles of sulfuric acid in the original solution. So 0.05 molar or moles per liter multiplied by the volume of the solution. And therefore the molar concentration of sulfuric acid in our final solution is the number of moles divided by 125 mils. So that gives 0.01 molar. And for every mole of sulfuric acid, we have 2 moles of hydronium in the solution. So therefore the concentration of hydronium is 0.02 molar. And from that, the pH of the solution is minus the log of the concentration of hydronium ions, where the number of decimal places is equal to the least number of significant figures in the problem, given we used a logarithm. Weak acids react with water to produce hydronium ions, but the molecules of the weak acid only partially ionize, whereas the reaction of a strong acid goes to completion. So therefore we have an equilibrium reaction, and only a small percentage of the molecules of a weak acid ionize in a solution. So the concentration of the hydronium ions will be much less than the initial concentration of the weak acid, and a majority of the acid molecules remain unionized. And examples of weak acids are acetic acid, hydrofluoric acid, hydrocyanic acid, and generally conjugate acids of weak bases. So the ammonium cation is a weak acid as it's a conjugate acid of ammonia. So for this reaction, the equilibrium constant, also known as the acid dissociation constant, is written in terms of the concentrations of the products and the weak acid. And this is often shown as pKa, which is basically the minus log of the equilibrium constant. Weak bases react with water to produce hydroxide ions in solution, and only a small percentage of the molecules of a weak base will ionize. So the concentration of hydroxide in the solution will be a lot less than the initial concentration of the base, because most of the base molecules remain unionized. And examples of bases include ammonia and a conjugate base of a weak acid such as the acetate anion, which is a conjugate base of acetic acid. So here we have the solution of a weak base which is in equilibrium with its conjugate acid, and the equilibrium constant or base dissociation constant is written in terms of the products and the equilibrium concentration of the base. And we can take the log of the equilibrium constant, and we solve these types of problems similar to equilibrium problems. We can determine the percent ionization for a weak acid or base from the equilibrium constant being the base dissociation constant in this case, and the initial concentration of the acid or base. So for example, if we're given these two values, we can determine the equilibrium concentrations using an ice table, as we've done for typical equilibrium problems. Then summing these together, you'll obtain the following expression for the base dissociation constant. And typically the concentration of hydroxide ions in the solution is much less than the initial concentration of the base. So we can make the approximation that the term in the denominator is approximately equal to the initial concentration of the base. And once we obtain X, we obtain the equilibrium concentration of the hydroxide ions in solution, and then dividing this by the initial concentration of the base gives the percent ionization of the weak base. And if instead we had a weak acid, we use the equilibrium concentration of hydronium and the initial concentration of the acid instead. The ionization of 1.2 molar of acetic acid in water is described by the following reaction. Find the percent ionization of acetic acid in the resulting solution. Well, we're given the equilibrium constant and the initial concentration of acetic acid, so we can use an ice table. And before the reaction takes place, we have 0 molar of the products. And for every mole of acetic acid that dissociates, 1 mole of hydronium and acetate are produced. So therefore the equilibrium concentrations can be written as follows. And using the equilibrium expression and the acid dissociation constant, that's equal to the concentrations of the products on the concentration of the acid. And they're using the approximation that the concentration of hydronium is much less than the initial concentration of the weak acid. So therefore we can omit X from the denominator. And now solving for X, and therefore the percent ionization is equal to the concentration of hydronium on the initial concentration of the acid. And that gives 0.39%. The ionization of 1.1 molar of ammonia in water is described by the following reaction with the following base dissociation constant at 25 degrees. Find the pH of the resulting solution. Well, here we use an ice table because we're given the initial concentration of the base and the base dissociation constant. And before the reaction initiates, and for every mole of the base that's ionized, we have 1 mole of the conjugate acid and 1 mole of hydroxide being produced. And summing these gives the equilibrium concentrations. And now using the base dissociation constant, we have the concentration of the products on the equilibrium concentration of the base. And again using the approximation that the concentration of hydroxide is much less than the initial concentration of the base, we can omit X from the denominator, and then solving for X, and this is equal to the concentration of hydroxide. And from this we can obtain pOH, and then using the following relationship, we obtain the pH of the solution as follows. A neutralization reaction is a reaction between an acid and a base which produces a soluble salt and water. And there's 4 mechanisms that depend on the strengths of the acids and bases, and here we look at a strong acid reacting with a strong base. And the strong acid and base completely dissociate in an aqueous solution. And getting rid of the spectator ions, we obtain a net ionic equation. And you may be given the concentration of the acid and the base and the volume of the acidic and basic solutions, and from that you'll be able to obtain a number of moles of the acid and base, and therefore the moles of hydronium and hydroxide. And therefore if the acid is in excess, the hydroxides will all get consumed, and you'll have an excess concentration of hydronium in the solution, and therefore the pH is determined by the concentration of the hydronium ions. And if instead the base is in excess, you'll be able to obtain pOH, and then use the following equation to obtain a pH at 25 degrees. And if you have an equimolar solution, then all of the hydronium and hydroxide ions will react, and you have a neutral solution. When a weak acid reacts with a strong base, we get a neutralization reaction, and a negligible amount of the weak acid dissolves compared to the strong base. So when we write the complete ionic equation, we assume that only the base dissociates. And eliminating the spectator ions, we have the net ionic equation. And if you're given the initial concentration of the acid and the base, then you can work out the number of moles. And in this particular case, the weak acid is in excess, so all of the hydroxide reacts, and you're left over with some amount of the weak acid. And the remaining weak acid molecules donate a proton to water, and you'll determine the concentration of the weak acid and weak base in a solution from the neutralization reaction, which you start off with here. And then from this, you'll be able to work out the equilibrium concentration of hydronium in the solution, and then you can work out the pH of the solution. And when you have a weak acid in solution with its conjugate base, you have a buffer solution which has a very stable pH. We determine the net ionic equation for a weak acid reacting with a strong base, and we assume very little of the weak acid dissociates in the solution. So in this case, we look at the strong base being in excess, so therefore the number of moles of the weak acid is less than the number of moles of the strong base. And we determine the concentration of the hydroxide ions from the leftover number of moles that are left unreacted and the total volume of the solution. And from this, we can determine the pOH and then use the following equation, assuming a temperature of 25 degrees, to obtain a pH of the solution, which will be basic. And note that we ignore the contribution of the conjugate base of the weak acid, because there's going to be a much less amount of hydroxide resulting from the reaction of the conjugate base with water. We write the net ionic equation for the reaction between a weak acid and strong base, and this time we're looking at the equimolar case. We have an equal number of moles of the weak acid and strong base. So therefore all of the acid and base is going to be neutralized till the conjugate base and the conjugate base then accepts a proton from water to yield the conjugate acid and hydroxide. And from here you can use an ice table and the equilibrium constant for the reaction to find the unknown concentration of hydroxide. And therefore you can find the pOH and then find the pH of the solution at 25 degrees, which will be slightly basic given there's hydroxide in the solution. When a weak base reacts with a strong acid, the strong acid fully ionizes, while the base accepts a proton from the acid. And from this complete ionic equation, if we get rid of the spectator ions, we obtain a net ionic equation. And we can write this in an equivalent form, where we add H2O to both sides, and in the case where the weak base is in excess, the acid gets fully consumed, and the remaining base molecules accept a proton from water to yield the conjugate acid and hydroxide. And now we construct an ice table, and use the remaining concentration of the base and the conjugate acid left over from the neutralization reaction, and use the base dissociation constant to work out the amount of hydroxide in the solution, and then use that to calculate pOH, and then a pH of the solution can be obtained from the following expression at 25 degrees Celsius. And note that when a weak base and its conjugate acid are present in a solution, a buffer is formed which has a very stable pH. We determined the net ionic equation for when a weak base reacts with a strong acid, and where the strong acid is in excess, the base gets completely neutralized, and we can obtain the pH of the solution directly from the concentration of hydronium ions. Now note that the conjugate acid can donate a proton to water to yield hydronium plus the conjugate base, where these are in an aqueous solution. But the concentration of hydronium from this reaction is much smaller than that obtained from the dissociation of the strong acid, so therefore this approximation of the pH, ignoring the contribution of the conjugate acid, is accurate. Using the net ionic equation that we derived with the reaction between a weak base and a strong acid, where we have an equimolar solution of the weak base and strong acid, then all of the base and acid are going to be neutralized, and we're left with the conjugate acid, which donates a proton to water to yield hydronium, and the conjugate base to this acid, where these are in aqueous solution. And from here you can use an ice table and the acid dissociation constant to find the unknown concentration of hydronium in the solution, and from that you can find the pH, where the solution will be slightly acidic. When a weak acid and base are mixed, they'll reach an equilibrium state, and we can represent the reaction by the following equation, where the acid donates a proton to the base, and we have the conjugate base of the weak acid and the conjugate acid of the weak base. Now given that strong acids and bases dissolve more, then if the strong acid and base are on the left hand side, then their concentration will increase in the solution and the reaction would shift to the right. And to determine if the solution is acidic or basic, then what you do is obtain a base dissociation constant and the acid dissociation constant. So for example, A minus being a conjugate base would accept a proton from water to yield an acid and hydroxide. And similarly, the conjugate acid would donate a proton to water. So this reaction would have a base dissociation constant, and this one would have an acid dissociation constant. So therefore, if Kb is greater than Ka, then the pH is greater than 7, and vice versa. Find the pH of a solution that's formed by mixing 50 ml of 1.8 molar of hydrofluoric acid with 50 ml of 0.9 molar of sodium hydroxide. So first we write the neutralization reaction, which yields a salt and water, where these are in aqueous solution. And ignoring the spectator ions, and assuming little of the acid dissociates compared to the strong base, we obtain the following net ionic equation. And now we calculate the number of moles of the weak acid and the strong base, and therefore the weak acid is in excess, so the concentration of the weak acid in the solution is the difference between the two on the volume of the solution. And now the remaining acid reacts with water by donating a proton, and now we construct an ice table using the molar concentrations from the neutralization reaction, and now you can use the equilibrium expression and the approximation, and we obtain the following concentration of hydronium. And therefore the pH of the solution is the minus log of this value. Suppose we have the titration of a strong acid with a strong base. So according to this titration curve, the pH is quite low, and as the base is gradually added in the solution, it increases gradually until the equivalence point is reached, where the number of moles of acid is equal to the number of moles of base in the solution. or the acid is completely neutralized by the base. And a strong acid-base neutralization reaction yields a neutral salt and water, so at 25 degrees, the pH is 7 at this equivalence point. And if we're using the known volume of the titrant, which is the base, for which we already know the molar concentration, we can calculate the number of moles of the base, and then using the mole ratios in the reaction, we can calculate the number of moles of the acid and divide that by the known volume of the acid to get the unknown molar concentration of the acid. And as more base is added, the base is in excess and you get a gradual increase of pH of the solution. We have a weak acid in an aqueous solution, and that reacts with water to produce hydronium and its conjugate base. So therefore this is a buffer solution. And now we titrate with a strong base, and that'll be neutralized by the acid to produce the conjugate base and water, and therefore the concentration of the conjugate base increases, and the buffer acts to shift the reaction to the left by Le Chatelier's principle to produce more of the conjugate acid. And therefore we initially see the buffer causing a gradual increase in pH, and at this point half of the acid is neutralized, and therefore there's an equal concentration of the acid and its conjugate base. And if we're using the equilibrium expression for this reaction, these will cancel, and if we take the minus log of both sides, we can obtain the acid dissociation constant by reading the pH. Now if we continue to add base, and at the middle here is the equivalence point, where all the acid has been neutralized, and the volume of base that's added at this point is double that at the half equivalence point. Here we have a buffer solution produced by a weak base, which reacts with water to produce a conjugate acid and hydroxide. And this is titrated with a strong acid to produce the conjugate acid at the base. And through the common ion effect, by Le Chatelier's principle, the reaction shifts to the left to create more base to neutralize the acid. And that's how a buffer has a very stable pH. And we can write the base dissociation constant for this reaction. And at the half equivalence point, half the base has been neutralized, so the concentration of the base is equal to the concentration of the conjugate acid. And therefore these cancel, and taking a log of both sides, we obtain the following expression. So we can read the pH at this point, and then use the following expression at 25 degrees Celsius to obtain pOH and the base dissociation constant. Now if we continue to add acid, the pH keeps dropping, and the buffer gets broken until we reach the equivalence point, where all of the base has been neutralized by the acid, and you keep getting a drop in pH as more acid is added. Consider the titration curve for carbonic acid. So this has two equivalence points, which tells us that the acid is diprotic. And at the half equivalence point, within the buffer, the concentration of the weak acid is equal to the concentration of its conjugate base. And we can also determine pKa by reading the pH of the curve. Now at the equivalence point, all the acid has been consumed, and we're left with the conjugate base. And it's the weak acid resulting from the titration of carbonic acid with sodium hydroxide. So at the half equivalence point, within the next buffer, the concentration of this acid is equal to the concentration of its conjugate base. And similarly, at this point we can determine the acid dissociation constant by reading the pH. So we'll call this 1 and 2. And at the equivalence point, all the acid has been consumed, and we're left with the carbonate ion being the conjugate base. A 10 ml 1 molar solution of a weak base is titrated with a hydrochloric acid solution, and in part A we'll estimate the base dissociation constant. So the buffer reaction can be written as follows, where these are an aqueous solution, and from this we can obtain the base dissociation constant, and at the half equivalence point the concentration of the base is equal to that of the conjugate acid. And using the following expression we can read off the pH, and therefore pOH is 4. And solving this equation gives the concentration of hydroxide, which is equal to the base dissociation constant. Now in part B, we'll find the molarity of the hydrochloric acid solution, and recalling the neutralization reaction of a weak base with a strong acid, where these are an aqueous solution. So at the equivalence point, all of the base is neutralized by the acid. So effectively the number of moles of the base is equal to the number of moles of the acid. And if we make our substitution, and the volume of acid that was added at the equivalence point, we get the molarity of the acid. Consider the following strong acids, ordered from the strongest, being perchloric acid, to the weakest acid, being nitric acid. And therefore the conjugate bases to these acids are ordered from strongest to weakest in the reverse direction. Now we can determine the relative strength of these acids from their molecular structure. So for example, if we look at the simple binary acids, their conjugate bases are stabilized by electronegativity, And as we know, electronegativity increases in this direction. And the difference in electronegativity between the atoms causes an inductive effect, or induced charge. So therefore the more electronegative conjugate base is going to result in a larger dipole moment, and this makes it more difficult to give up the proton. And resonance is another factor that determines the strength of the acid. So for example, nitrate has 3 resonance structures, and therefore the negative charge is distributed uniformly around the oxygens, and therefore either of the oxygens can bond to a proton, which makes nitric acid the weakest out of the 3. Carboxylic acids are a common class of weak acid where there's a carboxyl group attached to an R group. And typical examples are formic acid, where you have a formate ion that bonds to a proton, and acetic acid. So here we have the carboxyl group, and that's attached to a methyl group. So again, using the stability of the conjugate bases by considering electronegativity and resonance to determine the strength of the acid. Well, the conjugate base of formic acid has the following dipole moments, and so does the conjugate base of acetic acid, being the acetate anion. Now carbon is slightly more electronegative than hydrogen, so you'd also get the following dipoles, and therefore the methyl group induces a negative charge on the carboxyl group in the case of acetic acid. And therefore acetic acid is more effective at holding onto the proton, so it's the weaker acid of the 2. And note that these conjugate bases have similar resonance structures, because this double bond can form with either oxygen. Strong bases, which are ionic solids at room temperature, completely dissociate in an aqueous solution. And here we have ionic bonds between the alkali metals and hydroxide ions, and because the lithium cation has a smaller ionic radius than the sodium cation, which has a smaller ionic radius than the potassium cation, then potassium hydroxide will be the strongest out of the 3, because it more easily dissociates, thereby giving a higher concentration of hydroxide in the solution. Now if we look at the alkaline earth metals, these dissociate into 2 hydroxide ions for each metal ion, but these types of bases are not highly soluble in water, and we expect that strontium hydroxide would dissociate more easily because of the larger ionic radius, and therefore this would have a higher basicity than calcium hydroxide, due to the higher concentration of hydroxide ions in the solution. Common weak bases include the nitrogenous bases such as ammonia, and carboxylate ions such as acetate. So here ammonia is the stronger base because it can easily accept the proton using this lone pair to create a more stable acid, being the ammonium cation. And here acetate accepts a proton on either of these oxygens because it has those 2 resonance structures to form acetic acid. And if we compare the dipoles of these conjugate acids, so this polyatomic ion has a tetrahedral configuration, so it's non-polar, whereas acetic acid is polar. But you have these opposing dipoles, so acetic acid will give up that proton more easily, making it the stronger conjugate acid out of the 2. And stronger acids have weaker conjugate bases. We can determine the acid dissociation constant for this buffer reaction. We have a weak acid and its conjugate base present in the solution. And if you take the minus log of both sides, well, we applied the addition rule for logarithms, and then this here is the pH. So we can rewrite this equation as follows. And this relationship tells us the protonation state of the acid. So at the half equivalence point, where the concentration of the weak acid is equal to that of its conjugate base, then the log of 1 is 0, and the pH is equal to pKa. And if the concentration of the acid is less than that of the conjugate base, then this term is greater than 0, and therefore the pH is greater than pKa, which is somewhere here. And if the concentration of the acid is greater than that of the conjugate base, then this term is less than 0, and therefore the pH is less than pKa, which is for this case to the left of the half equivalence point. We can also use this relationship between the pH, which we'll see is known as the Henderson-Hasselbalch Equation, for a buffer that's created from a base. So what we do is replace the concentration of the conjugate base with the concentration of the base, and the concentration of the acid with the conjugate acid. And now for the case where the concentration of the base is equal to that of the conjugate acid, we have the half equivalence point where the pH is equal to pKa. And if the concentration of the base is lower than that of the conjugate acid, then pH is less than pKa, because the log term would be negative. So that would indicate this point where the solution is more acidic. And if the concentration of the base is greater than that of the conjugate acid, then this term here will be positive, and the pH would be greater than pKa, indicating the solution is more basic. Acid-base indicators are weak acids that change colour according to Le Chatelier's principle. So a typical example is phenolphthalein, which is colourless in a protonated form, and the colour changes slowly to pink-red when the solution becomes less acidic. So these typically have complicated chemical formulas. So in an acidic environment, you have the concentration of hydronium being higher, and that drives the equilibrium to the left. Whereas in a basic environment, the excess hydroxides react with hydronium, thereby reducing the concentration, and the equilibrium shifts to the right. So the indicator basically changes colour when the pH is equal to pKa, and in the case of this indicator, that's equal to around 9. So if you consider a weak acid strong base titration, we expect that the equivalence point has a pH greater than 7, so this is a good indicator to use. So what you do is add a few drops of the indicator in the titration, and then choose an indicator that matches the pH at the equivalence point of the titration to obtain a most accurate endpoint. A buffer can be created using large concentrations of a weak acid or base and its conjugate. So for example, if we have a solution of acetic acid, well, we can place its conjugate in the solution in the form of a salt, being sodium acetate. And a buffer can also be created by adding a strong base to a weak acid. And this salt's highly soluble in an aqueous solution, so it will dissociate into the following ions. And therefore you have acetic acid and its conjugate base, being the acetate anion, in the solution without neutralizing each other. Now if we are to place an acid in the solution, then the conjugate base would react with that acid to neutralize it, thereby increasing the concentration of acetic acid in the solution. And conversely, if a strong base is added to the solution, then acetic acid would neutralize that strong base and thereby create more of the conjugate base. And these reactions are responsible for the capability of the buffer to stabilize its pH. Consider the equilibrium equation for a buffer created from a weak acid. So the acid dissociation constant can be written as follows, and taking a minus log of both sides, we obtain pKa on the left. And now we can apply the rules for logarithms to break up this log, and this term here is the pH. So we can write the expression relating pKa to pH as follows. And this equation can be rearranged, and this is the Henderson-Hasselbalch equation. So adding small amounts of acid or base to a buffered solution does not significantly change the ratio of the conjugate base to the acid, and therefore won't affect the pH much. Now in a similar way, you can relate pOH to pKb using the equilibrium equation for this buffer created from a weak base, and in the reverse reaction, we can also write an expression relating the pH to the acid dissociation constant of the conjugate acid. Find the pH of a solution that's formed by mixing a weak acid with a strong base. So this neutralization reaction can be written as follows. So the number of moles of the weak acid can be calculated from the given values, and for the strong base, and therefore the molar concentration of the excess weak acid in the solution is the difference in the number of moles over the total volume of the solution. And if we write this in the form of the net ionic equation, while eliminating the spectator ions, we see that for every mole of the base that was consumed, 1 mole of the conjugate base was produced. So the molar concentration of fluoride can be calculated as follows. Because we have a weak acid and strong base reaction, we have a buffer, so we can use the Henderson-Hasselbalch equation to calculate the pH. And noting the buffer reaction, so if we make our substitutions, which gives a pH of 3.3. So as expected, the solution is acidic, given there's excess weak acid in the solution. We have the Henderson-Hasselbalch equation relating the pH of this buffer to the acid dissociation constant. And for the case where the concentration of the acid is equal to the concentration of the conjugate base, increasing these at the same time would not affect this expression. And therefore, the pH stays constant, but the capacity of the buffer is increased because you have more acid and its conjugate base to neutralize any added acid or base. If the buffer has more acid, then it has a greater capacity for neutralizing an added base than an added acid. So effectively the hydroxides are neutralized by the acid. And conversely, when the buffer has more conjugate base than acid, then the buffer capacity is higher for neutralizing an added acid rather than a base. So therefore, to create this buffer, it's best to choose a weak acid with a minus log of the acid dissociation constant, or pKa, is close to the desired pH.